All right, section 4.4 is called the definite integral. This is going to pull us back a little bit into section 4.1 where you were integrating, right, doing antiderivatives. You guys know what I'm talking about?
Yeah.
Good. And it's also going to pull us back into what we were doing in the last section with area under curves. So this is going to combine those two sections together. First of all, when we say something is integrable, we have a function for any function f defined on the interval a to b. The definite integral of f from a to b is this notation that we've been sort of playing with on your calculators a little bit before we started looking at this. This is the integral notation. It's got that script s here going on. The a and the b are the lower limit and the upper limit of your function right here. dx tells you with respect to what variable. In this case, we're doing this with respect to the variable x. And what you see this to be is from the last section. Do you see that delta x? You guys remember working with delta x in section 4.3? Do you remember adding up a whole bunch of function values, heights of rectangles?
Yep.
Yeah? And what this does then is it tells you that you're taking the number of rectangles and you're letting the number of rectangles go to infinity. So you're getting infinitely many rectangles underneath that curve, which you don't want to calculate all by hand, of course. But that is the limit. I should say the limit of those rectangles is the integral, that is the actual area under the curve from a to b. And it works no matter what the values are of c1 up to cn, as n goes to infinity anyway. When the limit exists, we say that f is integrable on ab. And the first handy theorem about all of this is that if you have something that's continuous, then it's integrable. And we've talked at length about continuity back in chapter 1. And then theorem 4.2, it does what we had happen in limits, when we first talked about limits. And when we first talked about derivatives, it says that if we have a function where we have two pieces that are added together and maybe they're multiplied by a coefficient, it's possible to pull the coefficient out in front, just like we did here, and to separate this into two separate integrals with the addition. And subtraction would be the same way. There's nothing special about plus versus minus here. Now the second sort of bullet point here is a little bit different. What it tells you is that if you have a location between A and B and you wanted to find the area, let's say, let me draw a picture just to visually demonstrate this. So here's A, here's B, and there's some C in between them. That if we wanted the integral, from A to B, what we could do is, if there was a need for it, is we could break this apart into two pieces and add the two pieces up. Right? And C doesn't have to be halfway in between or anything like that. At any point in between would work.
It just has to be the same.
Mm-hmm. And this might be very helpful if we had something that was maybe like a hole in the graph, or maybe the graph is continuous but it changes function, changes the equation of the function, like a piecewise graph or something like that. This would be a very helpful feature to be able to use.
So the C value is in between A and B?
Yes, the C value has to be in between A and B. And so you see down here, the notation changes it, right? So from going from A to B, we go from A to C, and then C to B. All right, so are you ready to combine all of your knowledge in Chapter 4 thus far?
Ready.
Or at least some of the pieces of it. All right, here's a function. We've got x cubed minus 1. And what we're going to do is we're going to actually calculate this area. Now, this one doesn't ask us to calculate. Let me take a step back. It says to give, this should say an area interpretation of the integral. All right, so here's what we're going to do. We're going to start with a picture of the graph. So go ahead and take your calculator, or if you know what this graph looks like, you don't have to have your calculator. What does the graph of this function look like? Obviously, it's cubic, right? Between 0 and 2, what happens? What happens at x equals 0? What's the value?
-1.
-1, thank you. So the y value is -1 at x equals 0. What's the y value at x equal 2?
3, 4.
Nope,
No. Oh no. 7.
7 is correct. It's over here at 7. So this graph does in fact cross the axis in between. Can you tell where? On your picture, can you tell?
Which axis?
The y, the x-axis. Where does it cross the x-axis?
1.
It does cross at 1. So the graph looks something like this. Roughly? Are we good so far? Okay. This is the first picture that I've drawn for you of this idea where it's crossed the axis. Everything I drew before was all completely above the axis. Agreed? Okay. So I want to bring this up because I want you to recognize what happens when you cross the axis. I want you guys to do this in 2 steps so that you can tell me what happens. You guys know some wonderful, cool features, either using function integration or using Math 9, using Math 9, which is function integration, or using your graphing screen. Here's what I want you to do. This half of the room, okay, so everyone let's go from Lucas over this way. I want you to integrate this from 0 to 1. Okay, so use Math 9 or use the graph, and I want you to go lower limit 0, upper limit 1. Over on this side, I want you to use a lower limit of 1 and upper limit of 2. So we're breaking it apart in the middle there, which we know we can do because we just have to emphasize that's possible. So we're going to break it apart, and I want you to tell me what happens when you do that. Okay, so let everybody have a chance to put everything in if you need to. Yeah, still working.
I said, what'd you tell us on
0 to 1. I'm sorry, Chance. I misunderstood. Yes, from 0 to 1 on your side of the room. Yes. It doesn't want us to solve. No, we're going to write down a description here in a minute of what's going on. So I think the next one we solve for it. No. I don't think we're even going to solve in this chapter. 4, 5 before we get to solve one of these puppies. Bummer. It's a bummer. We're just interpreting in this section, it looks like. Okay. What's that? Okay. I want to do that side of the room first. You guys went from 1 to 2. What happened when you got, what kind of an answer? Let me just actually write down the answer. What did you get to go when you went from 1 to 2? Okay. Now, the other side of the room, over here, what happened when you got your interval from -0 to 0 to 1? Negative 0.75. So that seems sort of weird. This is area, and you got a negative number, right? Any guesses as to what might be happening, or what your calculator does, or what this calculation actually finds when you do this?
area under x-axis?
Yes. So anytime you're working with area under the x-axis, you get a negative number. And anytime you work with the area above the x-axis, you get a positive number. Now that sort of gets hidden if we actually went from 0 to 2. So take your calculator now and find the area flat out from 0 to 2, and you're going to get a positive number. Why? Because what? It combines them, and we have more of it above on this particular graph, right? So you can't actually see that if you just went from 0 to 2. What this actually does is it finds I call it net area. sort of the area above minus the area below is what it actually does. So let's actually write down an interpretation of what's happening. So this calculation is the difference in the area trapped between the x-axis and the curve from 1 to 2, and the area trapped between the x-axis and the curve from 0 to 1. It finds the difference. Literally what it really does is this calculation, that is this notation, what it really does is that anything that's underneath the axis is negative area and anything that's above the axis is positive area, and it just combines the two values together. Okay? So that's what this notation is going to do. Now, obviously, if everything had been above the x-axis, there would be no difference in any of this, right? It would just be all positive area. There wouldn't be a, oh, this is positive area, this is negative. There wouldn't be any of that. But this one actually crossed the x-axis, so we end up with that sort of a feature going on. All right, so we're going to do the same kind of thing. That is, we're going to be interpreting and describing things in the second one.
So for the first problem, are we just supposed to draw the graph, basically?
It wants you to give an area interpretation. It wants this kind of an argument. Yeah. So interpretation is going to mean language involved with describing. But the picture helps you to make that decision. Without the picture, I'm not sure you're going to be able to give an interpretation, at least a sketch for yourself.
Could you say that again, though, like in black and white? I'm still not just kind of
Yeah. So what this calculation does is it finds this area, and of course I just made a mess of it, but it finds that area, and it finds this area, and it does this area minus this one, like in terms of actual area. That calculation right here actually finds the two areas and it combines them. Area above is positive, area below is negative. So it's kind of the difference between the trapped area. Yeah.
So for like our homework, do we have to write that out?
Yes. And it doesn't have to be verbatim what I just wrote in black, but there needs to be something about the fact that you're taking two areas and you're finding the subtraction between them. The area above minus the area below.
The only difference between each explanation is going to be the points, basically.
Yeah, it's going to be very similar. Let me clarify that just a second, Will. If the picture looks like this, what happens if your picture actually crosses the graph twice, the x-axis twice, or maybe doesn't cross it at all? So then your interpretation would be different based on how many times it would cross the x-axis.
So if it doesn't cross at all, then it's just one area.
Yeah, if it doesn't cross it at all, it would just be one area. What if it doesn't cross it at all and it's all underneath the graph?
It's still just one area.
Yeah, it's still just one area, but it's giving you sort of the negative amount of area that's actually there. That's what the calculation actually finds.
When you're talking about taking the difference between those two values,
Uh-huh.
would it be like adding them, though, since that bottom's a negative?
Well, yes, but it's the difference in the actual areas. This calculation actually, yes, it does the subtraction, but when you subtract the negative area, it ends up being added together. Yeah. Yeah, exactly. All right. All right, number 2 wants us to write the given total area as an integral or sum of integrals. So it says we want the area above the x-axis and below the graph of y equals 4 minus x squared. So in order to do this, we've got to graph it. I mean, that's the only way we're going to get the image that they're describing. What does this graph look like?
We're an upside down parabola.
Upside down parabola. What else?
And its maximum is at y equals 4.
Okay, on the y-axis too, right?
Oh, yeah.
Yeah. Something like this? this is the image. We want the area above the x-axis, below the curve. And in a very real way, in this one, it almost looks like the area that's being trapped. Can you picture that? It's looking like they're describing this piece right here. What am I going to need to know in order to calculate the area of that piece right there?
Your x-intercepts.
Yeah, I need to know the x-intercepts. Because I don't want it to continue down and then calculate area underneath the curve, because that's not what I'm asked for in this graph. So I need to know the x-intercepts. How do I find the x-intercepts for this graph? There's a couple of things you could do. Trace would be an option.
Table, just plug in.
You could use a table and plug in what you think are approximate values or pretty close to the values.
Factor.
You could factor it. You could even, without factoring, do it. But you're looking for where this is equal to 0, right? So you're exactly right. We could factor this as 2 minus x, 2 plus x. Finding out that x is plus or minus 2. Or from here, you could separate this so this says 4 equals x squared and square root it. So x is plus or minus 2. As long as if you're tracing or if you're using a table, that's fine too. Just be careful to make sure that what you're approximating the graph to be really is what it does. It doesn't end up being sort of like 3.1 instead of 3 or something like that. I think you're going to be working mostly with whole number values, so you won't have a problem. But all right, so this notation is supposed to be written as an integral. That's the script S. With the lower limit of -2, which we just found. The upper limit of +2, which we just found. The function goes inside. What's the function here? 4 minus x squared. And any time you're doing this, you're going to write dx or dy. Whatever your variable is, it's going to say d and then that variable at the end. This notation right here is notation that tells you what the graph's variable is that you're working with. And I know for right now that feels kind of silly. Well, obviously the variable is x because that's the only letter in my equation. I get that. The problem is that as you go further along in calculus, you'll have multiple variables inside of that, and you have to be able to identify what's going on, and it's a little different. So we're establishing that sort of a premise right now, that every time you use a variable, you write d with the variable on there. Okay?
Are we doing U substitution this semester?
Yep, 4.6. Okay, any questions on this one? The answer is simply what I just boxed in. That's the answer to the question. That's what it asks you to calculate. All right, next one is going to go backwards. We want to sketch the corresponding area to the integral. So I've got a graph. It's x squared minus x. And I want the graph to go from 2 to 4. Now, your graph itself can show more of the graph than that. But the shading for my graph will only go from 2 to 4. Okay? So take your calculator and let's just put it in a standard window, like -10 to 10, -10 to 10, something like that. So you can start with that. What does this graph look like? It is a parabola. Can you tell where the parabola crosses any of the axes? One spot should be pretty clear.
0 and 1.
Yep, the origin is one of them. And then the other one is over here actually at 0, 1. So I think the graph looks something like this. Does that look reasonable? You could have less of this picture showing, but you do need to have at least as much of the picture showing as starts at 2 and ends at 4, because those are the upper and lower limits of integration that you're working with, 2 to 4. So all this particular question's asking you to do is to identify the 2 and the 4 and where they are along the curve, and then shade in this area underneath the curve.
not like making a rectangle with these.
Nope. No, we're actually finding them exactly, or we're about to find them exactly in 4.5 for finding the areas for these without rectangles. Okay. The next problem we're going to do is giving us a few pieces of information to start with. They tell us 3 integral values. The integral from 2 to 4 of x cubed is 60, of x is 6, and of dx, or 1 dx, if you want to put a 1 there to give yourself an image, is equal to 2. Now, in section 4.5, we will calculate how they came up with the 60, the 6, and the 2, and how that came about. But for right now, we're going to use that information to make a decision, okay? What we're going to be doing is we've got this integral, from 2 to 4 of 4x cubed minus x minus 7. And what we're going to do is we're going to use this theorem back here, 4.2 part A, or part 1. This theorem says that if we have functions that are added, we can separate the additions. If we have constants that are multiplied, we can factor them out in front. Okay? That's what we're going to do on this particular equation, or expression. So we're going to recognize that this is subtraction, which means I can do 3 separate integrals. Okay, is everybody good with that so far? The next thing we're going to do is we're going to take each piece at a time. So this is 4x cubed. I'm going to put the 4 in front and the x cubed inside. The next one's just got minus x, which means I've got minus or a minus 1 if you prefer in front, and then I've got an x. And the last one says minus 7, which means the 7 can come in front and the 1 can go right here. 7 times 1 is 7. Why? Well, the reason that we did that is because we have values that we are given for those 3 pieces of information. So I'm going to have 4 times, what is the integral? Oh, let me get these in, sorry. This says 2 to 4, so all of my limits are from 2 to 4. What is my integral from 2 to 4 of x cubed dx? It's 60. So I can simply take 4 times 60 minus 1. Now, the integral from 2 to 4 of x is 6 minus the 7. And then the integral from 2 to 4 of 1 is 2. This should feel a lot like what you were doing with those summation rules on about half your problems last time. Do you remember that? Where you were factoring things out in front, you were using a summation rule on how to do the summations. It's very similar to that theory, or to that problem. What does this give you?
220.
220 is correct. So, yeah, this line right here, I expect to see you write out that line. Okay? That's what's showing that you're using that particular rule, that property, that factoring things out, that separation of the three different integrals. All right, one last problem. We are going to calculate something, but we're not going to do it using calculus. We're going to do it using geometry on problem number 5. It says use a geometric formula to compute the integral. So the first thing we need to do is we need to actually take this graph and take a look at it so we can figure out maybe what geometric formula they might be referring to. So you can use your calculator if you need or want, and you want to get the graph of this from 0 out to 2 of 3x plus 4. That's an equation that looks like a line. A line that crosses the the y-axis at what value? 4. And what is the value at x equal to 2? Can you tell? Plug in 2.
10.
10, thank you. So it looks like this. And we're supposed to be finding the area under this right here. there's at least 3 different ways to do this problem. So, what do you guys see? If you were given this shape and you were asked to find the area, which is exactly what you're asked to do, what would you do to do that? Luke?
Can we use any of the geometric components? I'd use like left or right, so left or right rectangle.
You can use left and right. I think there's an easier way to do it directly, though, with geometry, like high school geometry stuff, before we did rectangles like that. Do you have an idea, Noah?
Yeah, either trapezoid or dividing a triangle and a rectangle.
Those are the 2 most popular options. So one option that Noah said is to think about this as a trapezoid. Do you guys remember trapezoids? Trapezoids have parallel lines, sides, and this one does, right, along the x or the y-axis, and then along the line x equal to 2. If you think about this as a trapezoid, the way you find the area of a trapezoid, it's 1/2 base 1 plus base 2 times the height. So the bases are the the bases are the parallel line parts. So how long is the first base on the left? It's 4. And the base on the right is 10. The height then is going to be this distance right here, yes, which is 2. All right, calculate this, you get 14. Now, if you didn't see the trapezoid, or maybe you saw it after we said it, but that's not how you thought about it, another really popular way to think about this is to think about it as a rectangle and a triangle put together. In particular, here's the rectangle, and then here's your triangle. And I would tend to argue that put on the spot prior to 3 minutes ago, some of you probably wouldn't have remembered the formula for a trapezoid. But you probably all remember the formulas for areas of triangles and rectangles. So that's sort of the benefit of doing it the other way. So we've got the rectangle part plus the triangle part. So the rectangle then would be length times width, which would be what on this rectangle?
4.
Yep, 4 times 2, so you get 8 for that piece. Triangle, the area is 1/2 base times height, right? So the base would be this piece right here, or this piece right here, one of them. One of them is the base, one of them is the height, depending on your perspective of what you're looking at. So what do you get for those 2 values?
2 and 6.
Yeah, one of them's 2, and one of them's 6. So if you do 1/2 times 2 times 6, you get 6. And the total, combining the 8 and the 6, is the same 14 we had before. So between triangles, rectangles, trapezoids, those kinds of images are what you're going to be looking at for the geometric interpretation questions, okay? Any questions on that? All right.